Video, I'll be talking through the solutions to question 1 from the 2015 exam paper for Maths of Graphics and Virtual Environments. So question 1 presents you with a problem where you've got a spherical object with radius r and it's centered at Q, is moving with velocity v in the general direction of a point at P. So part 1, in terms of the vectors p, v, q and the scalar r, what condition is satisfied when the sphere collides? And show how this condition leads to the quadratic equation. So first thing you should really do is draw a diagram. So here I've drawn the diagram. So this is my centre of the spherical object Q. Okay, it has radius r, and it's going to be travelling along V, so it's going to be travelling along this direction. And here's my point P. So at some point, when in the future, I don't know when, the centre of the sphere is going to be at C when the sphere collides with the point object at P. Okay, C is described by the vector equation of a straight line, Q plus T times V, where T can be thought of as time. Okay, we have a collision. The sphere and the point collide when the distance between P and C is the same as R. Okay, so the distance between P and C is simply given by the magnitude of the vector P minus C. Okay, so because C is equal to Q plus TV, okay, we can replace C in this equation with Q plus Vt. Notice we have the minuses because we've got minus C. And I've got R squared here simply to avoid the square root. Okay, so if we rearrange that, and we want to rearrange it so it's in a quadratic formula in terms of t, so we have something times t squared plus something times t plus a constant. Okay, relate the three different types of real solutions this quadratic may have to the discriminant of the quadratic in three different collision, non-collision scenarios. So the three different scenarios are, we have a scenario like we've got here, where the sphere will collide with P, but as the sphere keeps carrying on, it'll collide once on the sort of the entry, and as the sphere continues, it'll collide once on the exit. Okay, we could have a situation where P is around where I've got the mouse pointer now, where the sphere will just collide once and just like graze the sphere. Or if P is where my mouse pointer is now, the sphere is going to miss entirely. So it's either collide twice, collide once, or miss entirely. Okay, so if we look at the quadratic formula, okay, so this is should be well known. So if A is coefficient of t squared, b is coefficient of t, and c is a constant, when the discriminant b squared minus 4ac is negative, we have no real solutions, so we have no collision. When it's equal, it should say 0 there, it's a slight typo. So when it's equal to 0, there's only one real solution, so it collides once, and when it's positive, there are two real solutions, and it collides twice. If there is a collision in the case where you've got values for Q, V, R and P, at what time does it occur? So is there a collision? So slight typo there. Okay, so we need to calculate A, B and C, which are straightforward calculations. I won't go through them here. Okay, insert A, B and C into the discriminant formula, and we have 24, which is positive. So we have two collisions. Use the quadratic equation to calculate T, and we have two values for T. 1.18 and 1.32, so the collision occurs at the smallest of those two values, so therefore it's 1.18. Okay, question part B, you'll get presented with 3 points and given the three tuples for each of those vectors, position vectors. So write out equation of a plane that is a linear combination of vectors. Since P2 minus P1 and P3 minus P1 are different, so not equal to each other, we say that these two vectors are linearly independent, so the point of any position of any point on the plane, and I've called it R, is equal to P1 plus a linear combination of those two vectors. Part 2, find the normal vector. We'll just take any two vectors, so any combinations of these vectors minus each other, calculate the cross product, okay, and we get 20 minus 5 and 5. Well, the question, notice it asks for unit vector, so we need to calculate the magnitude and simply divide our vector by its magnitude. And third part, write out a vector equation of the plane using this normal vector. Well, the vector equation of the plane is r dot n equals s, where r is any point on the plane and n is a normal vector. S is simply a scalar quantity. So if I use r equals p1 from up here, so 1, 2 and 4. Okay, so if I dot product my normal vector, which is there, by 1, 2 and 4, I get 30. So n dot r equals 30. And this is an equation that describes any point on the plane. R will have the same dot product with n as this, so it will always be 30.